All right. Yeah, thank you, Yoko, and thanks to the organizers for the opportunity to speak today. And a special thanks to Mirko Kurti for trading times with me. My power company kindly notified me that they're going to be shutting off power later this morning to repair the electricity lines in our neighborhood. So I traded to an earlier time to make sure it doesn't black out during the middle of my talk. So today, yes, I'm going to be talking about galaxy gas phase metallicities, both how we measure these at high redshift and how we're improving the systematics on that process, and also the results we have with the current data on constraining galaxy formation and growth using these metallicities. So just a quick definition, for me, metallicity is always going to refer to the gas phase oxygen abundance of the ISM in this talk, given by 12 plus log over 8, O over H. So that's what you'll see in the plots just as a definition. So by way of motivation, we've seen some of these simulations already. The buildup of the dark matter properties of galaxies is very well understood in the lambda CDM cosmological framework. But the buildup of the baryonic content is much more difficult to get a handle on because of the very complex interactions that the gas undergoes moving both into and out of galaxies, being moved around by feedback and energetic injection from supernovae and black holes. And so we want to understand this baryonic growth process, but it's a very difficult process to get a handle on. And so in our analytic theory of galaxy formation, we've simplified this to a few key parameters in a very simplistic view that includes the gas accretion rate into the galaxy, the star formation rate in the galaxy, then also the gas outflow rate from outflows that are driven by feedback within the galaxy. And in particular, what I'm going to talk about today is how the gas phase metallicity, the ISM, can be used as a probe of this process, because each step of this process modulates the metallicity in the ISM. And in particular, this picture highlights that there are two physical mechanisms that act to set the gas phase metallicities in galaxies. So effectively, the stellar metal yield, which is the amount of metals produced by supernovae and injected back into the ISM, sets what's effectively an upper limit on the metallicity of galaxies. And there's two mechanisms that act to lower the metallicities to the value we observe. So the first is on the left, metal dilution, and this is associated with the gas fraction of galaxies. And in this, newly produced metals are mixed into a larger gas reservoir if the gas fraction is larger, and so you get a lower metallicity. And this is associated with the gas accretion rate. On the right, we have the metal removal mechanism, and this is associated with a parameter called the mass loading factor of the outflows, which is just the outflow rate divided by the star formation rate. And of course, outflows can remove metals that are newly formed from the galaxy, but the feedback also acts to regulate star formation and thus slow down the production of metals in nucleosynthesis, thus again leading to lower metallicities. And so this is associated with the gas outflow rate as the key parameter. So later in the talk, I want you to keep these two mechanisms in mind. And in particular, it's the scaling of metallicity with global galaxy properties such as mass and star formation rate that have really informed our picture of galaxy growth and formation. So here I'm showing the two major scaling relations that have helped us here, the mass-metallicity relation on the left and the fundamental metallicity relation on the right, which is a relation that relates metallicity, mass, and star formation rate as well. And this is shown for data at redshift 0. And in particular, the mass-metallicity relation has shown us that outflows are important and required to explain the way the galaxies evolve, and in particular, that outflows are more effective as you go to lower masses, shown by that power law drop-off in the metallicity. But the fundamental metallicity relation shows us that gas accretion in this metal dilution process is also important. So galaxies at fixed mass that have higher star formation rates presumably have higher accretion rates to feed the gas for that star formation, but they have lower metallicities due to the metal dilution mechanism. And so this is illustrating the cycle of baryons process that governs galaxy growth. But at high redshift, galaxies have properties such as higher star formation rates, presumably larger cosmological accretion rates, many properties that make them very interesting laboratories to study baryon cycling because they're more intense than what we see in the local universe. And so we'd like to know, what do these relationships look like at high redshift, and what physical mechanisms control their shape and control their evolution over cosmic time. And so to do that, we need accurate measurements of metallicities in the high redshift universe. And so what I'm going to talk about next is how we measure gas phase metallicities at high redshift, and in particular, this sticky problem of metallicity calibrations that we've heard mentioned a few times in questions and discussions already. So in the local universe, the way we measure metallicities for the most part is by using these calibrations, strong line ratio calibrations. And you form these calibrations with a small sample that has measurements of what we call the direct method metallicity. It requires a measurement of the electron temperature through these weak auroral emission lines, such as the famous oxygen 3 4363 angstroms line. And so on the left here, I'm just showing one of these metallicity calibrations for redshift 0 H2 regions, relating the direct method metallicity to a line ratio, in this case, O3/N2. And we can do this for a whole host of line ratios. So all of the existing calibrations are based off of redshift 0 data sets. And so the question for us is, do these calibrations apply at high redshift? And it's not just a question of, we don't know the answer to that question. We actually have evidence from other things, such as evolution, the BPT diagram, that suggests that, in fact, we are pretty sure these calibrations are going to evolve with redshift. And so the question is, how do they evolve with redshift? And so the way we've been approaching this problem is by using deep spectroscopy to detect these weak auroral emission lines at high redshift. This is very difficult because these lines are about 100 times fainter than, say, H alpha. And so you have to work very hard to detect these with near-infrared spectrographs, for example. So I've just shown some examples here, some from my work and others in the literature, of oxygen 3 auroral emission lines. There's one in the REST optical. There's also one in the REST UV around 1663 angstroms. And so the combination of work in recent surveys, as well as with the literature, has assembled a small sample of 18 galaxies that have these direct method metallicities with a medium redshift of 2 in the high redshift universe. So here's what the sample looks like. This is for 2 line ratios, R23 and O32, versus the direct method metallicity. Now you can see the sample size is currently small, and many of these are low signal to noise measurements just above the detection threshold. So signal noise of 3 to 5 for many of these things, leading to large error bars. And so I wouldn't go so far as to fit lines through this and say, hey, we made calibrations, the problem is solved. But what we've been doing in the meantime is comparing the average of this high redshift sample to different calibrations from local data sets to understand what works and what does not. And so here the black diamond shows the average of the high redshift sample. And I'm comparing to a few things here. And I want to highlight this green colored line is actually constructed from extreme local galaxies that are analogs of redshift 2 galaxies. And you can see that that calibration actually seems to reproduce the properties of the redshift 2 sample quite well. But the typical samples we would use for metallicity calibration, say like normal H2 regions in the black line, does a very poor job of reproducing the high redshift data set. And so the lesson we've learned is that we should be very cautious about using normal redshift 0 calibrations to get high redshift metallicities. But these calibrations based on local analogs appear to work pretty well. And so that's what we're using in the meantime recently. But the future is very bright here, and James Webb is really going to be the answer to the first high redshift metallicity calibrations. I'm happy to say that we have an approved program for 64 hours on near spec to measure direct method metallicities for 50 galaxies at redshift 2 to 4 with what we're calling the Aurora survey. And I'm just showing a simulated spectrum from near spec from our program here, where you can see detection of multiple of these weak auroral emission lines for different ionic species. And so these observations with James Webb are really going to provide us with the first metallicity calibrations in the high redshift universe. But to convince you that this is an important problem, the TAC thought it was important enough to approve 3 different programs working on direct method metallicities at high redshift. Our own, one from Mirko Kurti, we're going to hear from Mirko in a couple of talks, and then also one from Alison Strom and Gwyn Rudy. So this is a significant investment during cycle 1 for James Webb, but it's going to have a big impact on our science. And to sort of do the TV commercial thing of, but wait, there's more, James Webb is also going to provide us with metallicity calibrations into the epoch of reionization. And how are we going to do this? So James Webb is going to measure these rest optical line ratios from, H alpha, oxygen 3, et cetera, up to very high redshifts of 7, 9, even up to redshift 12. But we still don't know what calibrations we should use to turn those into metallicities in the high redshift universe. These lines like oxygen 340, 363 are not feasible in the epoch of reionization because they would take more than 50 hours per target typically to detect. But a cool way we can do this is actually by combining the far infrared oxygen 3 lines as measured from ALMA with the rest optical oxygen 3 lines measured from James Webb, from which you can again determine the electron temperature and get a direct method metallicity. And the great thing is that ALMA has already shown the ability to detect these oxygen 3 far infrared lines in, for UV bright sources, only a few hours on source. And so it's a very promising method. And so I'm again happy to say that we have a cycle 1 approved program where we're going to measure the rest optical lines for 3 targets at redshift 6 to 7 that have 88 micron detections in ALMA and get the first direct method metallicities and anchor the metallicities in the epoch reionization with this small calibration sample. So there's a really bright future with James Webb, both at intermediate redshifts and at the very highest redshifts. Thank you. So now moving on, I just want to briefly touch on some of the results that we have in applying what we've learned about the calibrations at redshift 2 to the existing data sets. So I'm going to be using data from the MOSFIRE Deep Evolution Field Survey, the MOSDEF survey. This is a large survey with Keck MOSFIRE that obtained rest optical spectroscopy for about 1,000 galaxies at redshift 1.5 to 3.5. And in particular, the depth and breadth of this survey gives us a nice representative sample of these redshifts. And I'll just highlight that the spectra are actually publicly available and publicly released. So you can check out the MOSDEF website if you'd like to use these. So we get large representative samples at high redshift. I'm showing 2 samples here at redshift 2 and 3, just showing these are main sequence galaxies. This is star formation rate versus stellar mass. And we have large samples of hundreds of galaxies at each of these redshifts. And so what we've done is taken these calibrations based on analogs of high redshift galaxies I showed earlier. We've derived metallicities at redshift 2 and redshift 3 and gotten a new view of the mass-metallicity relation at these high redshifts with larger samples than we've been able to do this before. So this is what it looks like at redshift 2 and 3. Also have averages in bins of stellar mass that you can see in the larger data points. And so if we collect this together with redshift 0, we can look at the evolution of the mass-metallicity relation out to high redshift. We find a couple of interesting things with this comparison. First, the low mass slope is remarkably redshift invariant across this redshift range. We find that the slope does not evolve essentially at all. And as far as the normalization evolution, we find a slow but smooth evolution about 0.1 dex per redshift all the way out to redshift 3, which is consistent with what we see in modern cosmological simulations. So we've taken this mass-metallicity relation and applied chemical evolution models to place constraints on the mass loading factor of the outflows, which is what I'm showing in this plot here, mass loading factor as a function of stellar mass. Again, we find that the scaling with stellar mass is consistent over this redshift range because the low mass slope of the mass-metallicity relation is consistent. And in fact, the slope that we find, stellar mass to the power minus 0.35, is very, again, consistent with what's seen in simulations such as the FIRE simulation. Also agrees with the scaling that we see in direct observations of outflows at redshift 0 from rest UV absorption lines. At fixed mass, we find that the mass loading factor actually increases with redshift, which tells us that metals are actually more efficiently removed from galaxies at high redshift than they are at redshift 0. So this indicates that outflows are even more effective at high redshifts. Thanks again. So I'm going to move on very quickly. I'm not going to talk too much about this slide for the sake of time, but we basically find that the slope of the mass-metallicity relation is set by the scaling of the mass loading factor with mass and not by the scaling of the gas fraction with mass. It seems like the mass loading factor dominates. But if we look at a second plot here, trying to figure out which physical mechanism is responsible for the evolution with redshift, so in the plot here, I've shown in the purple line the fraction of the evolution due to changes in the mass loading factor normalization. And in the dotted green line or aqua colored line, the fraction of the evolution due to this metal dilution mechanism through the gas fraction evolution. And we find that each of these account for roughly half of in the mass metallicity relation. And so both metal removal and metal dilution evolution are very important for driving the metallicities of high redshift galaxies low to the values that we see. Finally, to wrap up, I'll just touch on the evolution of this fundamental metallicity relation. When Filippo Minucci published the FMR at redshift 0, he speculated that it might not evolve all the way out to high redshifts. And so we want to test this hypothesis with our new data. So here I'm showing redshift 0 data color-coded by star formation rate. And these left and right are just two different formations of the fundamental metallicity relation. And in particular, the right one, the x-axis is a linear combination of mass and star formation rate that is minimizes the scatter in this relationship. And if we plot the high redshift data on top here, we see that there's essentially no offset of the high redshift data from the redshift 0 fundamental metallicity relation. And if you look at the residuals down here, the residuals are very small actually. And so this tells us some interesting things that this equilibrium condition of galaxy growth appears to apply all the way out to redshift 3. And it actually suggests that there's a non-evolving framework in which the baryonic growth of galaxies proceeds over the past 12 gig years of cosmic history. So these new metallicity measurements using new calibrations that we understand better now have really been informing our interpretation of these large spectroscopic surveys. And the future with James Webb is really bright to increase the accuracy here and get into an epoch of precision metallicity studies at high redshift. So I think I'm a couple minutes over, so I'll wrap up there. Thank you.